In this video, we're going to discuss another set of rules for nomenclature, naming chemical compounds. In this case, we'll be talking about naming ionic compounds. Out of all four groups, naming ionic compounds is probably one of the most complex. There are a lot of different scenarios to deal with, and we need a set of rules to deal with every single one of those scenarios. Let's start by talking about some quick learning objectives. First of all, we'll go over what an ionic compound is, some of the basic concepts and rules behind this. Later in the year, we'll take some time and go over this topic in a little bit more detail and understand the mechanics behind it. But for now, you just need a basic understanding. And you need that understanding so we can identify ionic compounds. As with all naming systems, the first step in the process is knowing what type of compound you're naming first, and then being able to apply the appropriate set of rules. So we'll talk about some rules on how to identify an ionic compound versus acids, covalent, and hydrates. Next, we'll get into the actual naming rules themselves. As I mentioned before, there are a lot of different scenarios to consider when dealing with ionic compounds. We'll talk about how to name simple ionic compounds first. We'll then deal with something new known as polyatomic ions and how we account for them in names. And then finally, we'll deal with something known as Roman numerals. We use Roman numerals in names for ionic compounds. We'll identify when those Roman numerals are needed and how they're actually used. Finally, to wrap this entire process up, we'll go over some practice problems. I'll let you guys work on those on your own, and then we'll discuss the answers. Let's begin with a discussion of what ionic compounds are and why atoms form ionic compounds. To start, when you're having an ionic compound, we're dealing with an exchange of electrons between two atoms, and this is what actually goes about forming the bond. When you have atoms exchanging these electrons, it ends up turning them from atoms into something new, known as ions. An ion is any atom with a net positive or net negative charge. Now, as we mentioned before, that exchange involves a couple things. Some atoms, for example, are going to gain electrons, and let's get rid of that there. As a result of gaining those electrons, these atoms are going to have a net negative charge. Remember, electron itself has a charge of -1. Electron itself has a charge of -1, and as a result, it's going to gain a negative charge by having extra electrons. Other atoms are going to lose electrons in this process of the exchange, and as a result, they're going to have a net positive charge for the same exact reason. If the electrons themselves have a negative charge and we've lost them, the end result is a net positive charge in the atom. This exchange occurs in order to make the atoms more stable. And that's what all chemical processes are going to be about this year, is going towards a state of increased stability. To be more specific, the atoms are gaining or losing these electrons in order to achieve something known as an octet. Now, this is a concept we're going to talk about in a lot more detail later in the year, and we talk about actual configurations of electrons. But what you need to know about an octet right now is that it represents completely filled electron orbitals or shells. This is when all the rings or all the places our electrons go, every so often we get to a point where they're completely filled. This represents the most stable electron configuration that an atom can have, and this ties us back to the idea we mentioned before, is that these atoms are gaining or losing these electrons to increase that level of stability. An octet just happens to be the most stable configuration. One last thing I want to talk about before we move on is the fact that in ionic compounds, the net charge of an ionic compound always must equal 0. So the question at hand is what does that actually mean? Let's talk about an example of a couple ions we can work with here. We can start with a sodium ion with a charge of +1 and a chlorine ion with a charge of -1. These two guys will combine, and we write them together next to one another, NaCl, to form a very familiar looking compound of sodium chloride. And the question is how did I know what that formula was? Well, the sodium, as we said before, had a charge of +1. The chlorine had a charge of -1. When we combine those two together, we end up getting a net charge of 0. And that's what we're talking about here. The net charge in the ionic compound must always equal 0. This helps us determine the formula for our ionic compound. Let's try another example, something a little bit more complicated. Let's try magnesium, which has a charge of +2, and chlorine, again, which has a charge of -1. When I combine the two of these together, we get Mg and Cl. The question is this the correct formula? Well, we look back and the magnesium had a charge of +2, the chlorine had a charge of -1, and unfortunately when you add these two together they add up to a total of +1. this is not a net charge of 0, which means this can't possibly be the formula for magnesium chloride. We need more of these negative charges, and the way we do that is by increasing the number of chlorine atoms or chlorine ions in our actual formula. And the way we're going to do that is by putting a little 2 down here. That's going to mean it's -1 and -1 combined. Those two guys combine, and this does eventually equal 0, meaning our formula for this compound containing magnesium and chlorine ions ends up being MgCl2. Let's take this one step further and do something a little bit more complex, and that'll be working with something like this. We can start with the yttrium ion, which has a charge of +3, and we can have the oxygen ion, which has a charge of -2. We're going to combine these two guys together, and we get YO. When we check the charges, we get +3 and -2 here, and again, this adds to a total of +1, meaning this can't possibly be the right formula. Now before, the solution was simply to double the number of chlorines until the charge is added to 0, but unfortunately this isn't going to work that way because the 3 and the 2 are never going to go into each other evenly. What we need to look for here is the least common multiple between the two of these. In this case, 3 and 2, the least common multiple is going to be 6. If I have 2 yttriums, that's going to give me +3 and +3 for the +6 that we were looking for. And if I have 3 oxygens, that's going to get me -2, -2, and -2 for the -6 we're looking for. Add that +6 and -6, and now we've got that charge of 0. None of this mathematics is terribly complex, but you can see how for some of these formulas you're trying to create, we're going to have to work a little bit harder than others. You got easy guys like ones over here, and then you've got more challenging ones like the ones we're dealing with. So next, the question you might have been asking yourself in that previous slide is, where are all these charge information coming from? Well, the good news is all this information can be very conveniently found on your periodic table. What I have over here is a blown up version of the element gold, and we can see right here are the charges listed for the element gold. In this case, we have an example of 3 being one of its possible charges and +1 being its possible charges. It's also important to note that even though it's never listed, all elements can also have the charge of 0. This is when they're in the pure element state, as opposed to the charges is when they're acting as ions. All the other charges possible are listed in each one. You'll notice one of them is bold. Do not make the assumption that the bold one is the one you're working with. Both the gold +3 and the gold +1 are viable options. You need to use the context of the problem you're dealing with to decide which one's the right one. Don't just assume it's always going to be the one that's bolded. Now let's talk about how to identify a compound as being ionic. Remember, before you try and name it, you have to decide that it's ionic first. Otherwise, you risk using the wrong set of rules to name your particular compound. So let's get some characteristics that all ionic compounds contain. First of all, ionic compounds can be identified by recognizing that it's always going to be a metal bonded to a non-metal. If you recall back from our periodic table, earlier in the year we took some time to identify key regions on the periodic table. This region over here, shown in pink, are all of our metals. This region up here in the corner, shown in yellow, are all our non-metals. If you've got one of your ions coming from here and one of your ions coming from here, you've got yourself an ionic compound. Second thing on the list, we haven't talked about these yet, but something you'll be looking for are things called polyatomic ions. These are these relatively complex looking structures here, all of which have a charge associated with them, and we'll have a list of these you can look at later. Eventually you'll get familiar with a lot of these and you'll be able to identify them, but in the beginning you're looking for strange endings. We're looking for a lot of things like ate endings and ite endings. When you see those other types of endings, that's when you should be looking for something that's known as a polyatomic ion. If it contains a polyatomic ion, it must necessarily be an ionic compound. Last, and these are easy to spot, if your name contains a Roman numeral in it, like the ones we have listed up here, then you also know you're dealing with a ionic compound. Only ionic substances have Roman numerals in them. All right, with these three things combined, you should be able to identify something as being an ionic compound, either in the formula or in the actual name itself. Our next order of business then is coming up with the rules for actually naming these compounds. I'm going to list the entire set of rules right now, and then later on we'll go through examples of each of the different scenarios. So some of the stuff right now might not make a little sense. Your job is to create the list of rules first, and then like I said, we'll sort out the details in later slides and examples. Just like with other types of compounds, ionic compounds have a first name over here and they have a last name over here. Underneath each of these, I'm going to write some instructions as to what the first name and last name are actually going to be. In the case of the first name, we're going to include, it's going to be simply the name of the positive ion. It's going to be the name of the positive ion, which in this case is always going to be our metal. And that's pretty much it. No changes, no modification, just going to be the name of that positive ion. The only thing you have to worry about sometimes is sometimes you need to also include a Roman numeral if your positive ion is listed as having more than one charge. So if your positive ion has more than one charge listed, let's underline that part there, more than one charge, then you have to include a Roman numeral, and that's going to happen after the first name. This is kind of a 50-50 thing, and we'll talk more about how to handle this Roman numeral issue a little bit later on. The last name, that's it for our first name then. The last name is going to be the name of your negative ion with the ending changed to IDE. It's going to be changed to the suffix "ide." The negative ion is typically your nonmetal from your compound. The only other rule we have to deal with the last name is that if your negative ion is polyatomic, then there's going to be no ending change. Again, we haven't talked about what polyatomic means yet, but as we identify it later, if you do have a polyatomic ion you're dealing with your last name, we're going to have no ending change. You're going to copy down the name as you see it on your actual sheet. Now, this is the general set of rules. Seeing the rules itself I don't think is necessarily super helpful. I think more than anything you have to see these rules in action a little bit. We're going to go through a couple simple examples first. We'll then talk about polyatomic ions. We'll go through some examples of them. We'll talk about Roman numerals, and then finally we'll go through some examples of them. At the end of the video, I'll have examples of everything all blended together, and that'll be an opportunity for you to really test how well you understood this. So let's get to some of those practice problems. These practice problems earlier on are ones that I'm going to want to do together. I'll give you ones that you can work on your own later on in the video. If you feel like you want to take a swing at these on your own, by all means pause the video and give them a try. But I think going through them together as a group might be very advantageous at this point. Let's think about our rules. We have our first substance here. We have our two ions. The sodium is going to be the first ion. The iodine is going to be the second. I think sometimes it's helpful to draw a line through them like this to identify the two separate pieces. When we deal with polyatomic ions later, you'll find that that's very valuable. Anyway, let's go through our rules. If you need to, look in your notes as I'm reading along with these. The first name of our compound is the name of the metal or the positive ion, and that metal is always listed first. Looking up Na on our periodic table, we find out this element is known as sodium. And that's it. Checking with sodium. We're going to hold off on the Roman numeral stuff for now. Let's just call it, let's leave it as sodium and move on. The second name for our compound is from the second element listed, the negative ion. In this case is the element iodine. We're going to change that INE ending to an IDE, and this becomes iodide. And that's the name we're looking for. This substance is known as sodium iodide. We'll go on a little bit further. Let's take a look at this next one. Same thing. We're going to separate the first and second elements here, and that's going to identify our two ions. Our first ion is Li. It's the element lithium. And then we look at our second one. This is the element oxygen. The ending changes to IDE, and we end up with lithium oxide. Sometimes it's difficult to know how much to chop off and replace with the IDE ending. Again, as you gain experience with this, there's only a couple elements that get that ending. You'll start to recognize what those patterns actually are. So these are two very simple examples of applying the rules from the previous page. Let's work these problems in the other direction. Here I've got names written down, and the goal will be to come up with an actual symbol for them. First one is going to be radium sulfide. So the first thing we want to do is come up with the symbols for each element. We look up radium on our periodic table. It has a symbol of Ra. We look up the charge that goes along with radium, and it has a charge of plus 1. We look up the second element. It is sulfide. That IDE ending suggests that it used to be something else. It is the element sulfur, and it has a charge of -2. If you recall from earlier, we've got to combine these together to get RAS, but we've got to combine them in a way so that the net charges add up to 0. Well, if we've got -2 here and only 1 plus 1 for the radium, if we had 2 radiums present, those plus 1 and plus 1 will cancel out the -2, and we get the formula Ra2S. Let's continue the process here. We talked about this example before, but now we actually have the name to work with. This is yttrium oxide. Again, on your periodic table, you look this up. We have the symbol Y for yttrium. We look up its charge, and it is -3. We have the symbol O for oxygen. We look up its charge. It is, oops, sorry, this is +3. Oxygen's charge is -2. We try to combine these two together to get the symbol YO, but as we talked about before, Y and O are never going to go evenly into one another. We can't just double the Y or double the O. We've got to come up with that least common multiple. If you recall, -2 and +3 have a least common multiple of 6. If I have 2 yttriums, that's going to get me the +6 that they have in common. If I have 3 oxygens, that's going to get me the -6 I have in common. And again, now we've got a net charge that adds up to 0. This was pretty quick. Again, we'll have practice problems at the end, and if you need more practice with this, there's tons of practice available. Getting good with these is really just a matter of practice. Moving on, now we're going to deal with some of the more complex issues that go along with ionic compounds. We're going to be talking now about polyatomic ions. Up to now, we just defined ions as being anything with a positive or negative charge, but it turns out that ions come in a couple different flavors. There are different types of ions out there. The ions you've talked about so far, or seen so far, have been monoatomic ions. These are charged particles that are made up of only one type of atom, so one atom at a time. These have been all the examples we've seen. Here's some examples down here: chlorine with the -1, magnesium with the +2, oxygen with the -2. All of these can be found on your periodic table, and that's exactly where you need to look these up. Now, the presence of monoatomic ions also necessitates that there must be something else. There must be a counterpart to this, and that counterpart are going to be polyatomic ions. Whereas mono means one, polyatomic means many, or in this case, multiple. These are charged particles that are made up of multiple atoms that are covalently bonded together. These atoms form a group, and that group follows the same rules as monoatomic ions. They have a charge. We have to get net charges add up to 0, and it's important to note that they behave as one cohesive unit. So even though these polyatomic ions are going to be made up of many atoms, they're going to behave as one charged particle, just like the charged particles we had from up here. Let's take a look at some quick examples of what I'm talking about. SO4 with a charge of -2. It's made of sulfur atoms and 4 oxygens, but it doesn't matter. This whole thing behaves as one ion with a charge of -2, much like the oxygen ion up here behaves as one ion with a charge of -2. Likewise, we've got this guy over here, NH4 with a charge of +1. It's made of 1 nitrogen and 4 hydrogens, but it still behaves as one group, one thing, and that one thing has a charge of +1, just like the ions we had from up here. We don't have one with a charge of +1, but it's going to behave very similarly. The important thing to note with this is that polyatomic ions look different, but they behave in exactly the same way. You are responsible for being able to work with these polyatomic ions, but you are not responsible for knowing them. You should have a table that looks very similar to this table right here, bonding relevant data. This table can be found at the bottom of the page associated with this video, or it can be found in my download section. I very strongly encourage you to stop the video right now, go down to the bottom, download and print this out. What you can see here is it provides you with the name of each of the polyatomic ions as well as the symbol, and at the top of each column we have the charge that goes along with it, but that charge is also listed with each symbol itself. As you work with these names, as you work with these formulas, you're going to have to reference this list pretty regularly to be able to figure out what the formula is for your polyatomic ion or what the name is for your polyatomic ion. Last thing to note, please notice that there are ions up here as well as a separate group of ions down here. This is just a list of common ones. This is a table that shows polyatomic ions grouped by the elements involved. Notice these are all nitrogen and oxygen-based compounds. These are all sulfur and oxygen compounds, and these are all chlorine and oxygen compounds. So make sure you're checking one of these two places in order to figure out which is the name of the ion you're dealing with. Let's dive right into some practice. Just like before, we're going to use the same set of naming rules, but now we're going to introduce this idea of polyatomic ions into the mix. So our first one here, again, we're going to separate the first and second ion from one another, and we'll use the same rules. The first ion, our positive, is our metal. That is going to have the name calcium. When you look it up on your periodic table, we look to the second piece. This is the element chlorine. I know there's a 2 here, but remember, it's not how many atoms there are, it's how many types of atoms. Our ion is only made of one type of atom, therefore it's monoatomic. And if you recall, the ending in this case changes to IDE. This chlorine becomes chloride, and that's the name we're looking for here. So this is nothing new. This is exactly the same as the examples we used from before. Let's take a similar looking compound and we'll talk about what this one is. So again, we separate the first ion from the second ion. Sometimes that is difficult to do, but again, as you become more familiar with your polyatomic ions, you'll be able to recognize that that separation becomes right here. Just like before, our positive ion is the element calcium. Now we look up here. This second element is made up of chlorine atoms and oxygen atoms. This is telling us that it is polyatomic. You should not be looking for this on your periodic table. You should be looking for this on your polyatomic ion sheet. And when you look up ClO4, you'll see that ClO4 has the name of perchlorate. The ending on the sheet is ATE, and remember we talked about with our original rules, when you're dealing with polyatomic ions, the ending does not change. You simply copy it down as is. So this just simply becomes calcium from our periodic table and perchlorate from our polyatomic ion sheet. Let's take a look at a couple in the other direction. Here we have ammonium bromide. Ammonium is one of the trickier ones to find. First of all, you should notice it is not an element. There's no ammonium on your periodic table. Looking then on the only other resource you have, you find out that ammonium is NH4 with a charge of +1. For some reason, people have trouble with this ion. It's the only positively charged polyatomic ion, and people tend to miss it. So NH4 +1, and again, we have our bromine. The IDE ending suggests that it is from our periodic table. In this case, it is the Br, and if you look it up, it has a charge of -1. We combine them together to get NH4 Br, and we have a -1 here from the NH4, and we have, a +1 from this, we have a -1 from the Br, and this is a completed formula. That net charge adds up to 0. So like to watch out for. Don't let this 4 fool you. Sometimes people think that this means there's 4 of these, in which case this is +1, +1, and +1. That is not the case. This 4 is part of the symbol for ammonium. We still only have one of those ammoniums. In the next example, we'll talk about how to handle situations where you have multiple of your polyatomic ion and how we handle these 4s down here in that scenario. And that brings us down here to our last example. Just like before, we have our positive ion, our negative ion. Magnesium, hopefully we recognize as an element at this stage in the game. You look it up, it has a charge of +2. Hydroxide has the IDE ending, but when you look it up on the periodic table, you're not going to find anything that matches this hydrox, in which case you need to look at your polyatomic ion sheet. Unfortunately, there's a couple of polyatomic ions with these negative endings, and this happens to be one of them. Its symbol is OH, and it has a charge of -1. Again, we combine these two together, and we get MgOH, but unfortunately the charges don't quite work out. We got a +2 there, and we have a -1 here. Like before, though, we can handle this in exactly the same way. We can put a 2 here to double the number of hydroxides we have, but unfortunately the way this is drawn, it makes it look like we have 2 H's, and we want 2 of the whole thing. The way we handle that situation is by using parentheses. So whenever you need to have multiple of one particular ion, you use parentheses around it and then put the number afterwards. As we can see from this, we now get the completed formula for the substance magnesium hydroxide, Mg in parentheses OH, close parentheses 2. Now let's talk about the last piece of the puzzle here. That's naming rules again, but now we're going to deal with Roman numerals. Roman numerals are used in names for ionic compounds when the cation, this is specifically only for the cation, the positive one, has more than one possible charge. And let me show you what I mean by that. Some elements, like for example ruthenium over here, have multiple charges listed. If I told you a ruthenium ion, you wouldn't know if it was ruthenium +2, ruthenium +3, ruthenium +4, ruthenium +6, and ruthenium +8. we need something in the name that's going to help us to differentiate between all of these different ions that are possible there. And we're going to use Roman numerals. Let me show you what I mean. If I just start with the name ruthenium chloride, you're going to look up ruthenium on your periodic table. We have the symbol Ru, but we're not going to know which of these charges to use. We'll then look up our chlorine. It has a charge of -1 and it'll be good to go. But unfortunately, we can't come up with a formula here because we'll never know how many chlorines or how many rutheniums we need to get the charges to balance because we don't know which of these charges is going to get the job done for us. The answer to that question is that this is not a very good name for ruthenium chloride. It's not specific enough to help us figure out specifically what ruthenium chloride we're dealing with. To fix that situation, we would include a Roman numeral. In this case, I'm going to put in the Roman numeral 2. What that Roman numeral 2 is telling us is that we're talking about the specific ruthenium with a charge of +2, in which case this is no longer a question mark. This is now the charge of +2. Now we can put things together and we can find out our formula will be RuCl2. We need 2 of the -1 chlorines to balance out the +2 from the ruthenium. Likewise, we could have had this name, ruthenium. Let's do ruthenium 6 chloride. What that's telling us is that when we look up ruthenium on our periodic table, now we want to choose this charge for it. This is going to be ruthenium +6. This is still going to be Cl -1, and we're going to end up with the formula RuCl6 as our net equation that has a net charge adding up to 0. So we use the Roman numeral not to tell us how many rutheniums there are, but to tell us which charge to use. So maybe we should write that over here on the right side of the screen here. The Roman numeral tells us which charge to use for our positive ion. And that's all it does for us. When you have an element that deals with this situation, you'll use the Roman numeral to figure out which charge to use. And then unfortunately, when you write names, sometimes those names are going to require you to use Roman numerals. So let's talk about how that works. Roman numerals are only needed when multiple charges are listed. You'll notice a lot of the names we've come up with so far, prior to that last slide, didn't have Roman numerals associated with them. They weren't wrong, they just didn't need them. Let's take a look at these two elements down here and compare the two of them. Ruthenium has many charges listed, +2, +3, +4, +6, and +8. Magnesium only has one charge listed. Ruthenium is going to always need a Roman numeral. We're always going to need to tell the person that's reading this which of the charges we're going to be using in this particular case, whereas magnesium, I don't need to tell people whether or not what the charge is going to be because my only option is the charge is +2. Magnesium will never need a Roman numeral. We don't need to warn the person about what that charge is. They'll already know. And since these charges never really change, every single magnesium compound will not have a Roman numeral. Every single ruthenium compound will have a Roman numeral. This is simply an extra check that you're going to need to make along the way as you're coming up with these names and deciding whether or not that Roman numeral is necessary, and then finally determining what that Roman numeral should be. Let's wrap this whole thing up by going over a couple practice problems. I'm going to let you try these practice problems on your own. See if you can fold in some of the stuff that we talked about before. In these ones, you want to get the names and convert them into formulas. Use the rules we talked about. You should have that rule back from earlier in the presentation. Pause the video and take a couple minutes to try these. On the next slide, we'll talk about the answers and go over why those answers are what they are. Here's a quick rundown of our answers. In this first scenario here, we have the substance strontium chloride. We look up the symbol for strontium. It is Sr. We look up the symbol for chlorine. That IDE ending tells us it's monoatomic, so we'll find this on our periodic table. It's just the element Cl. The charges were given for each. Strontium is +2, chlorine is -1, and we end up with the substance SrCl2. This one's pretty simple and pretty straightforward. We have a very similar name here. The only difference between the two is the fact that that was IDE and this is ATE. Whenever we have an ending other than IDE, that lets us know we're dealing with a polyatomic ion. You look on your polyatomic ion sheet and you find the symbol for chlorate as being ClO3. Again, the strontium still had a charge of +2. The chlorate had a charge of -1. We need 2 chlorates to balance that out, and as we talked about before, we use parentheses around this to say that we need 2 of these ClO3s. Lastly, don't let this 3 in here trick you. Doesn't mean that there's 3 chlorates. ClO3 is the symbol for the chlorate ion, just like strontium's symbol is Sr. This symbol just happens to include a number. Let's take another one. This one down here is a little more challenging. Yttrium dichromate. Yttrium we talked about earlier in the video. It is Y with a charge of +3. Dichromate again has that ATE ending, suggesting that it is not an element but a polyatomic ion. And when you look it up, you get this guy over here. It looks relatively complicated, but it doesn't matter. It's just a symbol. We don't care what these letters and numbers are in here. All we care about is that this guy has a charge of -2. And like before, these are 2 charges that don't go evenly into one another, so we had to find a common multiple between the 2 of them, and again, that's 6. 2 of the +3's gets us +6, 3 of the -2's gets us -6, and our net charge adds up to 0. The last 2 examples here deal with Roman numerals. We have iron. When you look up iron on your periodic table, multiple charges are listed, but in this case, the Roman numeral tells us what charge to use. This is iron with a charge of +2. Sulfate has that ATE ending, which means it's a polyatomic ion. When you look it up on your sheet, it has a charge of -2. These 2 charges are already balanced, so you just put the 2 pieces together. We get FeSO4 for iron 2 sulfate. Same problem, but now instead of being iron 2 sulfate, now it's iron 3 sulfate. In this case, we look up our iron. It still has multiple charges listed. In this case, though, we're told to use the charge of +3 as opposed to up here, where we use the charge of +2. Sulfate is still the same thing. It still has that charge of -2, and again, we've got to find that least common multiple to get these to balance out. 2 irons gets us a total positive charge of +6. 3 sulfates gets us a total negative charge of -6, and now our net charge adds up to 0. Let's try a few problems in the other direction. In this scenario, I give you formulas, and your job is to come up with names. I find in most cases, students find this a little bit more challenging. The rules are a little harder to use in this particular direction. Just like before, take some time, go through the problems yourself, pause the video, and then at the end I'll go over the answers together. Alright, here's our answers. Just like before, the first couple are going to be easy and they'll get harder as we go along. This first one here, Ca and Br2, we're going to split this into our 2 separate ions. This can be challenging in the beginning, but as you do more of this, you'll be able to identify them more easily. Ca is the element calcium. Checking on our periodic table, calcium only has 1 charge listed. It can only ever be +2. Therefore, we do not need a Roman numeral for this compound. Br is simply 1 element, meaning it's a monoatomic ion, which means we look it up on our periodic table, and we end up getting bromine, and we change our ending to IDE. So this one follows the simple rules we talked about back in the beginning of the video. In the next one, we'll do the same thing. We'll separate the positive ion and the negative one. 99% of the time, that positive ion is simply the first element, with the exception of what we'll talk about next. So you can draw the line there. Everything else must be the second element. There's only ever 2. So if you've identified this as being the first one, everything else be second. We look up on our periodic table. This is the element sodium. Sodium only has a charge of +1 listed, meaning we don't need to worry about including a Roman numeral. So we're going to leave that out. We just copy down the name sodium. NO3 is the symbol. If we look here, it's made of multiple atoms. It must be polyatomic. We look up NO3 on our sheet, and it is simply known as nitrate. We simply copy the name down. Because it is polyatomic ion, we have no ending change. So this ends up being sodium nitrate. Moving on, we take a look at another one here. This is the 1% of the time exception to what I talked about in the sodium nitrate problem. You need to recognize NH4 as being one of your polyatomic ions. If NH4 is one of them, everything else must be the other ion. In this case, we look up NH4. Its name is ammonium, as we talked about earlier in the video. And OH, we also talked about earlier in the video, as being the substance hydroxide. Polyatomic ions never need a Roman numeral, so in this case, we don't need one there as well. Let's take a look at our last couple examples here. We've got W, which is the element tungsten. Parentheses is a dead giveaway that you're dealing with a polyatomic ion. Everything else must be that polyatomic ion. Now, tungsten is an element that has multiple charges listed. In fact, tungsten has many charges listed. So we need to figure out what particular charge we're using here. We don't know the charge on tungsten, but we do know the charge of this NO2. On your polyatomic ion sheet, it tells you that NO2 has a charge of -1. There are 7 of them, which means our total negative charge must be -7. If you remember back to the rules earlier in the document we have here, the net charge has to add up to 0, which must mean the tungsten has a charge of +7 in order to cancel these two things so they add to 0. That explains how we came up with this Roman numeral 7 right here. So we have the first name tungsten, Roman numeral 7, and nitrite, because again that's the name our polyatomic ion data sheet showed us. Last example again is very similar. The parentheses give us a good idea as to how to split things. We look up Ni, it is the element nickel. Nickel has many charges listed just like tungsten does, so we have to take some time and figure out what the charge of this nickel atom is going to be. Just like before, we use the other ion to figure out that charge. This is HCO3. This is our bicarbonate ion. It's on our polyatomic ion sheet, and it has a charge of -1. There are 2 of them, which means our total negative charge now is -2. To balance that out, the nickel must be +2, so that everything again adds up to the number 0. That explains then why we have the Roman numeral 2 here. This must be nickel 2 hydrogen carbonate. That's one of the names for this guy. Or this is also known as nickel 2 bicarbonate. That is a second name for this polyatomic ion sheet here. Both of these are listed on your polyatomic ion data sheet. At this stage in the game, you should not yet be an expert on naming ionic compounds. This is complicated. There's a lot of things going on here, and this requires a significant amount of practice in order to be effective with it. There are tons of worksheets located at the bottom of the video. There are worksheets in my download section. You should definitely start sitting down with those and trying just ionic naming for now until you feel significantly more comfortable with these rules.